Hello, I'm Seema from Alobasics. I welcome you all for the next video on wave optics. In today's video, we'll discuss a very important topic from interference, that is Young's double slit experiment. This experiment is also said to be Young's double hole experiment. Young's double slit experiment is the first experiment to support wave nature of light. In 1801, Young has first time demonstrated the experiment of interference of light. And the setup for Young's double slit experiment is having source, convex lens, it is optional, then a opaque sheet or a plain cardboard having two slits marked on it and screen. We can use convex lens with source on its focus to get plane wavefront or parallel rays after convex lens, or instead of this we can place source at far away from this cardboard on which slits are there. This opaque sheet which we are using, on which there are two slits, these two slits are very narrow, about 2 to 4 millimeters size or width, and the separation between them is comparatively larger than that of the slit width. From this source, we get rays of light which are coming radially outward, or the wavefront which is coming on this lens. When it passes through the lens, we get parallel rays as source is placed at the focus of the lens, and as these rays are parallel, we say that the wavefront which is present here, that wavefront is plane wavefront. This plane wavefront, when it passes through these two slits act as secondary sources, producing cylindrical wavefronts with its axis along the slit length. And these wavefronts, we can see its cross section. So instead of cylinder, here we can see it in the form of circles. Now these cylindrical wavefronts superpose with each other and they produce interference pattern. From these wavefronts, we get interference pattern on screen. We get constructive and destructive interference, and this interference is observed due to the phase difference in the waves which are coming from these two slits. This interference pattern is in the form of bands of maximum intensity and minimum intensity. It is in the form of bands because our two secondary sources are linear sources. In this way, the setup of Young's double slit experiment is used. When we have to draw a diagram of Young's double slit experiment on paper, then that diagram can be drawn in this way. In this diagram, we have a source, then convex lens, two slits are placed, S1 and S2, which are separated by some distance. In front of that, at certain distance, screen is placed. In this diagram, you can see that there are few red dots and few blue dots. These blue dots are the combination of crest with crest or trough with trough. And if we join all these blue dots, we get maxima or bright. And red dots are nothing but combination of crest with trough or trough with crest. If we join these red dots, we get minima. We may get it as a point or fringe. Whether it is point or fringe, it depends on source. If source is point hole source, then we get points. If source is linear source, we get fringes. And these maxima and minima are said to be bright and dark also. This interference pattern actually on screen it observes like this. You can see bright dark fringes, and these fringes they are separated by certain distance. Fringe width is the separation between or the distance between two consecutive bright fringes or two consecutive dark fringes. Means from this to this or from this to this. Here we are taking the distance from center of one fringe to center of next fringe. And here to get clear bright and dark fringe, our source should be monochromatic. If source is not monochromatic, we may not get clear bright and dark fringes. We'll discuss this in video of conditions for interference pattern. To get more clear idea of propagation of wavefront in single slit and double slit, we'll see this picture. In this picture, you can see that here there are plane wavefronts and they are passing through an opening. This opening may be point source or a hole or linear source. If it is a hole, by passing through it, we get spherical wavefronts, and if it is a linear, then here we get cylindrical wavefronts. Now in picture, you can see its cross section that is in circular form. But depending on sources, it may be cylindrical or it may be spherical. For single slit, you can see that when it is passing through it, we get such type of circles on the other side of the slit. When it comes to double slit, then what happens? Let's see. Now here I have two slits, and from each slit, when plane wavefront is passing, then now these two slits are acting as a secondary sources. So here we get either spherical wavefront or cylindrical wavefront depending on the type of source, whether it is point or linear source. And these wavelets or these wavefronts from the two sources are superposing with each other to get combined crest with crest or trough with trough or crest and trough. Depending on that, we get either bright or dark, or we say that we get constructive interference or destructive interference. We have seen setup of Young's double slit experiment and how to draw its diagram on paper. Now, let us discuss its theory. For discussing its theory, first of all, we'll see geometry of this double slit experiment, and in this diagram, you can see that there is a source and source is placed in front of two slits S1 and S2, and for simplicity we'll consider that S1 and S2 are at same distance from S. Now in front of this slits there is a screen placed at distance capital D from these two slits. Two slits S1 and S2 are separated by distance small d. Two perpendiculars are drawn from S1 and S2 on screen as S1M and S2N. Separation between M and N is also D. Let us consider a point O on the screen. At this point, the rays or the waves from S1 and S2 will reach with zero phase difference. Due to that, we say that the distance traveled by the wave from S1 to O and from S2 to O is same, and this O will have maximum intensity, or we call it as bright point. This O is equidistant from M and N. Now, let us consider another point on the screen, P. This point P is such that waves from S1 and S2 will reach at point P with some phase difference. Now this phase difference will decide whether point is bright or point is dark. Now in this picture you can see that the distance traveled by the wave from S1 and S2 is not same, as due to that there is difference between these two distances, which we call as path difference, the path traveled by the waves. And this path difference is given by delta L is equal to S2P minus S1P. S2P is this distance and S1P is this distance. Now if I want to find out this path difference, then I'll consider two triangles in this diagram, that is S1PM and second one is S2PN. Both these triangles are right angle triangles, and in these two triangles S1P and S2P are their hypotenuse. So we apply Pythagoras for this, for finding S1P and S2P. First of all we'll go for S1P. S1P square is equal to PM square plus S1M square. PM and S1N should be known to us, and S1M is nothing but capital D. So I can write S1P square is equal to D square plus Y minus D by 2 whole bracket square. How I got this value? Let us see. PM is distance of point P from M point. Point P, we are considering that it is at distance Y from the central bright point or central maxima. So this PO is Y and MO is D by 2. So PM will be Y minus D by 2. So we can write this expression. Similarly, in second triangle S2PN, we can write S2P square is equal to D square, because S1M and S2N are same, plus Y plus D by 2 whole bracket square, because this PO is Y and ON is D by 2. So we can write this as D square plus Y plus D by 2 whole square. Now I got S1P square and S2P square. By subtracting these two equations, we get S2P square minus S1P square is equal to D square plus Y plus D by 2 whole bracket square minus D square plus Y minus D by 2 whole bracket square. Now we have to simplify this, and after simplifying this expression, we come to S2P square minus S1P square is equal to 2YD. How I got this 2YD? Here D square, this minus D square will get cancelled. Similarly, this Y square will get cancelled. This D square by 4, this D square by 4 will get cancelled. And what will left? YD from this and YD from this. So here we get it as twice of YD. As this expression on left hand side is in the form of x square minus y square, so we write it as S2P square minus S1P square is equal to S2P plus S1P into S2P minus S1P. This is just similar as x square minus y square is equal to x plus y into x minus y. Our aim is to find out S2P minus S1P. So we'll write this and we'll substitute value of S2P plus S1P in that, and S2P and S1P can be taken approximately equal to D, because this distance is very, very small, and due to that these two are approximately same. In addition, we can take it as D plus D as a 2D. By substituting these in equation of delta L, we get equation of delta L is equal to S2P square minus S1P square divided by S2P plus S1P, and substituting here values of these, we get delta L is equal to 2YD divided by 2D, that is equal to YD by D, and This is nothing but path difference for the waves when they are reaching at any point on the screen. Now this path difference we are using for deciding whether point P is dark point or bright point, whether we are getting constructive interference or destructive interference. Let us see how to decide point P is bright or dark point and how much is the separation between two bright or two dark points. This point P, it's said to be bright point or it's said to be bright fringe. Depending on type of source, either you will get point or fringe. If I'm considering P as a bright fringe, then when this will be bright, that we have to discuss first of all. It will be bright only when the path difference between these two is n lambda. Path difference, we have seen that it is yd by capital D, and if this path difference is equal to n lambda, where what is value of n? N is equal to 0, 1, 2, 3, 4. We know that O is bright fringe. As it is bright fringe, value of n is equal to 0 here. Or we say that path difference is 0. I told you waves from S1 and S2, when they are reaching at point O, they are traveling same distance. So naturally path difference will be 0 for this. So this point is said to be central bright or central bright fringe. Then next bright fringe we'll observe for n is equal to 1. Then next to that will be n is equal to 2, 3. And we have seen in interference pattern that we have alternate bright and dark fringes. So for this point P should be bright, path difference must be equal to n lambda. If this condition is satisfied, we say that point P is bright point. If path difference should be n lambda, then what should be this distance y? This distance y, I'm writing yn generalized equation, that is equal to n lambda d by d. From this equation, we are writing this equation. Our aim is to find out y. So y is equal to n lambda into capital D by d, and this is the distance of nth bright point on the screen from central bright. Again here we say that values of n are 0, 1, 2, 3. For first bright, second bright, third bright or nth bright, what will be the formulae? That we'll see here. Just what I have to do, substitute the value of n at 0, 1, 2, 3 like this. And for n is equal to 0, y0 is equal to 0, that is central bright fringe. y1, that is equal to n lambda by d. So this distance will be lambda d by d. For second, it will be 2 lambda d by d. For third, it will be 3 lambda d by d, and so on. For nth, it will be n lambda d by d. Here I am having number of bright fringes. My aim is to find out fringe width. What is fringe width? Fringe width is the separation between two consecutive bright fringes or two consecutive dark fringes. Separation between nth and n plus 1 or n minus 1 bright fringe. That will give me fringe width for bright one, and that fringe width is given by beta. This b is representing bright or maxima, which is given by symbol w, yn plus 1 minus yn. Now according to this, I can write yn plus 1 as n plus 1 into lambda d by d minus yn is n lambda d by d. By subtracting this, we get its value as lambda d by d. If point P is not bright but it is dark, what will be the separation between dark fringes? That also we'll discuss. Now I'll consider P as a dark point, and for point P to be dark, path difference is given by 2n minus 1 lambda by. For bright it is n lambda. Here it is 2n minus 1 lambda by 2. Values of n are from 1, 2, 3 like this. This can be considered as odd multiple of lambda by 2. Bright is an integer multiple of lambda. Here it is odd multiple of lambda by 2. If point P is dark, then what will be the value of yn? Yn is given by yn is equal to 2n minus 1 lambda d by 2d. Again, values of n are from 1, 2, 3 like this. Now, on the basis of this, for each value of n, we can write down how much is the distance of dark point from the central bright. If we have this P as a first dark point, then I'll get for n is equal to 1, this y1 dash is lambda d by 2d, because value of n is equal to 1, and this will become 2 minus 1, that is 1. So lambda d by 2d. For n is equal to 2, that is for second order, we have y2 dash is equal to 3 lambda d by 2d. For n is equal to 3, it will become 5 lambda d by 2d, and for n is equal to n, yn will be 2n minus 1 lambda d by 2d. So in this way, we'll get the values of y for different values of n. Now from this, again I want to find out fringe width for dark fringe, and it is given by similar type of equation as we have discussed for bright fringe, and we get expression for fringe width as beta d. D is representing dark. Again it is given by W, and that is equal to yn plus 1 dash minus yn dash. Here we'll substitute values of yn plus 1 and yn as per this expression, and we get it as 2n plus 1 minus 1 lambda d by 2d minus 2n minus 1 lambda d by 2d. And here again we come across the same result, that the fringe width for dark fringe, even it is given by lambda d by d. So from this we can see that fringe width for bright fringe or for dark fringe is same, or we can say the expression for fringe width is same. So fringes, whether it is bright fringe or whether it is dark fringe, they are equally spaced on screen. It is not that bright is wider or dark is thinner, but their sizes are same, their spacings are same, and due to that we can consider that fringe widths are equally spaced. We have seen that bright fringes and dark fringes are equally spaced, means their fringe widths are same, which are given by lambda d by d. Now as distance between two consecutive bright bands and dark bands is same, sometimes we require angular separation between them. This is required for solving numericals, and if we want that, then we have to find out angular fringe width. This angular fringe width can be determined by using angular separation between two consecutive bright or two consecutive dark fringes. For that, we require nth bright fringe separation from the central bright, and it is given in terms of theta, that theta is equal to yn by d. Here it is considered that theta is very small, so I can write theta is equal to tan theta, and that value we can find out as yn by d. Now the procedure for determining angular fringe width is similar to that for determining the fringe width, or to determining the separation between two consecutive bright or dark fringes. We'll find out first of all theta n by substituting value of yn from this equation, and we get theta n is equal to n lambda by d. We find out angular fringe width, that is equal to theta n plus 1 minus theta n. Here we'll substitute their values and we come to conclusion that angular fringe width is given by lambda by small d. Similarly, I can find out angular fringe width for dark fringe also. Same procedure will follow here, and here theta n again given by y by d, but value of yn is different for dark fringes, and that value will substitute from this equation. So we come to the equation that theta n is equal to 2n minus 1 lambda by d. Rest of the procedure is same. Angular fringe width is given by substituting all these values, and we come for the same conclusion that it is equal to lambda by d. Even we can see that angular fringe width is also same for bright fringe as well as dark fringe. As path difference is associated with any bright point or dark point, so as to phase difference also associated with that. So let us discuss on the relation between path difference and phase difference. Phase difference delta phi is given by 2 pi by lambda into path difference. We have seen path difference is given by yd by capital D. So we can find out phase difference by using this. We get 2 pi d upon lambda d into y. So using this, we can find out phase difference. As we know that for bright point and for dark point, or for maxima minima, or for constructive interference and destructive interference, we have different path differences. These path differences correlated with phase differences. For constructive interference, that is for bright band, we know that path difference is given by delta ln is equal to n lambda, where n is equal to 0, 1, 2, 3, and corresponding phase difference is given by delta phi n is equal to 2n pi. We get this value of 2n pi just substituting here n lambda. Lambda lambda will get cancelled, and what is left, that is 2n pi. Again, values of n are just similar to this, that is 0, 1, 2 onwards. Or in other way, I say that for constructive interference, path difference is integral multiple of lambda, whereas phase difference is even integral multiple of pi, because here there is a factor 2n. If point is dark, means interference is destructive. Then what is condition for destructive interference? For destructive interference, path difference delta n is given by 2n minus 1 lambda by 2, where values of n, now here it is starting from 1, not from 0. Keep in mind this thing. And corresponding phase difference delta phi n is 2n minus 1 pi. Again, I can get this value by substituting this value in this equation. Values of n are from 1, 2, 3, 4 like this. I can say that for destructive interference, path difference is odd integral multiple of lambda by 2, and phase difference is odd integral multiple of pi. If I am giving conditions in lambda by 2, odd integral multiple of lambda by 2, odd integral multiple of pi. Here also, if I want to give it in terms of lambda by 2, I say that even integral multiple of lambda by 2, even integral multiple of pi. It depends on you how you want to keep it in your mind. These are the conditions for constructive and destructive interference in terms of path difference and phase difference. As we have discussed fringe width, that gives me separation between the two fringes in terms of distance. Similarly, in terms of phase, how much is the phase difference between two successive bright or two successive dark bands is given by delta phi n plus 1 minus delta phi n, and it is 2 pi d upon lambda d. Same thing I am using. Now instead of y, here it will be yn plus 1 minus y, and we saw that the value of this yn plus 1 minus yn is nothing but the fringe width, and it is same for bright band as well as for dark band. Its value is given by lambda d by d. So we are substituting that value, and by calculating we come to the value 2 pi. The phase difference for successive bright or dark band is constant, and it is given by 2 pi. It is same for bright as well as for dark. As fringe width is same for bright or dark band, similarly phase difference is also same for bright and dark band. Or in specific way, I say that phase difference is same for successive bright and successive dark bands. Here I am giving you questions on today's topic. These are descriptive type of questions. If you solve these questions properly, it will help you for your board exam. Thank you for watching. See you soon in next video.